Our first session has two talks. The first talk is Gradient Descent for Randomized Controllers under Partial Observability by Linus, Spel, Sebastian, Junges, Moerman, Joost-Pieter, Katoen. And Kip is going to give the talk, right?
Yes, thank you. So I will talk today about gradient descent for randomized controllers under partial observability. And to start off, I will tell something about partial observability and controllers. So imagine you have, for instance, self-stabilizing protocol, or you have some autonomous system with self-driving cars, for instance. Then there is partial observability, meaning that we don't know the exact state of the system. And furthermore, there can be non-determinism. So we need some controller to resolve this non-determinism, and we will look at randomized controllers to do this. One question you could ask yourself here is, well, find a controller such that the probability of a crash is really small. And to do so, we normally model it by partially observable Markov decision processes. As with normal Markov decision processes, you have these actions and probabilities at the transitions. And furthermore, it's partially observable, meaning that we cannot distinguish between some states. So for instance, in this model, we cannot distinguish between state S1 and S3. We want to find a controller here such that the probability of reaching some given state is really small. And we need a randomized controller here because we cannot distinguish between states. To do so, we try to transform it into a parametric Markov chain. We can use this to either find a memoryless or a k-memory controller, but for this talk, I will focus on memoryless controllers. So how do we do this? Well, we try to look at states with the same observation, and at these states, we will take an action alpha I with probability pi. And this is, again, this randomization, and this probability then tells us what we have to do for this controller. So what does it look like? Well, we have our original pMDP, and we try to transform this into a parametric Markov chain. And when we start looking at state S0, we see we have three actions. An action alpha 1 we take with probability P1, action alpha 2 we take with probability P2, and action alpha 3 we take with probability P3. And you can see the transitions here with the probabilities. Next, when we look at state S1 and S3, we take these actions with the same probability. So at both state S1 and S3, we take action alpha 1 with probability Q1. And we now have a parametric Markov chain. So we transformed our model into a parametric Markov chain, and our goal will now also change. So we wanted to find a controller such that the probability of a crash is really small. We changed it in reaching some given state. And now we need to find the goal for this parametric Markov chain. And the goal here is to find parameter values. To be able to talk about how we find these parameter values, I will first go into the details of parametric Markov chains now. And there is some related work on this, particle swarm optimization and quadratic equals straight quadratic programming. These two methods have already been shown that they can actually find these parameter values. So next, parametric Markov chains. Here we see a parametric Markov chain. It's like a normal Markov chain. We have states. We have some initial state, in this case, state S0. Then we have a set of target states. In this case, our target state is the happy smiley, for instance. And finally, we have parameters and transition functions. And yeah, you can see that instead of fixed probabilities, these parameters occur at the transitions. For our parameters, we have some region in which they must lay. So for instance, in this case, a region could be that P should be between 0.4 and 0.7. And this is given. Next, we can also have rewards. So here we see an example of a reward function, and a reward function simply says, okay, when leaving this state, you get the following reward. So for instance, in this case, at state S0, you will get a reward of 2. Then we can define rewards for paths, where the reward for a path is just the sum of the rewards of the states we visited. So for instance, when we go from state, when we have a path S0, S2, happy smiley, then the reward will be the reward from S0 plus the reward from S2, because those were the states we left, so to say. For a infinite path, we can also define the reward. We need to define the target here. And if we eventually visit the target, then the reward is the finite part of this path. And if we will not eventually visit our happy state, then the reward will be infinite. Next, we can define the expected reward for a parametric Markov chain, which is simply the reward of the paths times the probability of this path. And finally, we denote this as a reward function, where you can see that we have the state we're interested in, and we want to go to the happy smiley. This is some notation. And then in the end, you end up with some value. And now a question we ask ourselves in this case is, well, we want to find the expected reward, and we want to find an instantiation. So we want to find values for our parameters such that the expected reward is, for instance, greater or equal than some threshold lambda. So for instance, in the example we saw before, we had it should be smaller than 0.001. So here you see a small example. You assume that there is some region given, a reward function is given, and we now might, for instance, ask ourselves, okay, we want the probability for a state, for instance, S0, to be greater or equal than 9. And then you can ask, okay, give me a value for P such that this holds. Recall that we were looking at probabilities. So we wanted to look at the probability of reaching some given state. Probabilities are actually a special case of rewards. When we're looking at probabilities, we assume that we have some happy state and some sad state. And of course, you want to reach the happy state. And we can transform this into a question with expected rewards, the following. Instead of looking at the probability, we now look at expected rewards. And instead of wanting to go to the happy state, we want to go to a new target state, happy prime. And we obtain this model. And now we do add rewards as follows. When we see the happy state, we say, okay, we give it a reward of 1. And when we see the sad state, we give it a reward of 0. And also all other states in between have a reward of 0. As you only get the reward once you leave this happy state, this will actually give us the probability, because the probability of going from S0 to the happy state, well, say it's 0.9 in this one, then it would be 0.9 here. And then we would get 0.9 times 1, our reward, for going here. And then we have the probability, so to say. So yeah, we will now focus on rewards, but note that we can also use it for probabilities. So now we have seen something on parametric Markov chains and rewards, and I'll now focus on gradient descent. So the main idea of gradient descent is to use the gradient of some function to find parameter values such that some requirement is achieved. So for instance, here we see a function, and we want to find a value for P such that we have a value for our function of at least 5.9. So let's say, well, we start at P is 1. Well, at P is 1, our function value will be 3.5, which is not fulfilling our requirement yet. So we will look at the gradient to see, see what our next P should be. Our gradient is 4, and well, we say, well, okay, we'll do something with its gradient. Let's add this gradient 0.1 times to our original value. So we get a value of 1.4. We now look at our function again. Well, it's almost 5. So we're not there yet. So we look again at the gradient. Well, we update our P. We get a new value for our function. And we see we're still not fulfilling our requirements, so we will update it again with a gradient. And now we finally find a value for our function. So this is the main idea of gradient descent. So we just look at the gradient. Then we were thinking, like, how can we apply this to parametric Markov chains? And we decided to also look at the derivative of a parametric Markov chain. So for instance, if we're interested in the expected reward of going from our state as 0 to our happy state, then, well, if we look at the gradient of this, we just use the product rule, and you see that's, well, the derivative of this can be written according to the product rule. And we thought, well, this seems quite similar to what we had before, because here you saw we had p times the expected reward of going from S1 to the happy state, and here we have this p time as well. And here we have the 1 minus p times the 1 for S2, which we had there as well. So we thought, why not take a copy? So that's what we did. We actually just created a copy, and yeah, we take the derived states, so to say. And then we look like, well, okay, what can we do with this? Well, here you again see, okay, this is this derived state S1. And, well, here we have this transition in here, so that's good. And then next we have this 1 time and minus 1 times, which you can see here. And we add them as well, and we can do this for all states. And then we actually get some derived weighted automaton, which we call. And yeah, this is the main idea behind what we did so far. So as you can see, that these are not probabilities anymore, because we have minus 1 and 1. I left out the ones with probability 0 because they are not interesting. And actually, we use this to solve our problem. And we observed that, well, if we take the derivative of our expected reward function we saw so far, then this is actually equal to the expected reward of this derived weighted automaton. So that's the main idea behind our approach. Next, we looked into some existing gradient descent methods. We looked into classical methods, which I will explain. We looked at some adaptive algorithms. And finally, we considered sign methods. So first of all, the plain method, this is the one we actually saw in the example before. We just look at our gradient, and we have some learning rate, in our case 0.1. And we just update our parameter at each round, and you will get this figure. Next, there is momentum gradient descent, where we don't only look at the current gradient, but we also look at previous change, which we weighted. And as you can see, we now only need 3 checks, so to say. So here we had 4 dots, and here we have 3. And as you can see, it actually kind of went over the real optimum. And finally, for the classical methods, we looked at the Nesterov accelerated, where we don't only look at the gradient, the previous change, but we also try to predict the next position. And this will help us to not go over the optimal value. So these were the 3 classical methods we considered. We also looked at adaptive algorithms, where the learning rate is based on what happened in the past. And we also looked at the sign method, where we don't take into account the exact value of the gradient, but only the direction. So we only look, do we need to add something to our parameter? Should we subtract something? Then we considered 3 different kinds of gradient descent. Stochastic gradient descent, meaning that we only update 1 parameter at a time. In batch gradient descent, you do all parameters. And with mini-batch, we only took a subset of the parameters and then went up to the next subset. We all implemented this. Then another issue what we had to look at were region restriction methods, because we are, of course, looking at parameters, and these parameters should represent probabilities. So we actually implemented 3 ways to ensure that these parameters are still representing the probabilities. The first one was projection, which actually works like a hard wall. So as soon as you get out of our region, we just map it back to our, for instance, upper bound. So for instance, if this would be the region for our parameter, and we would first be here, then we would go there, and then at the second iteration we would be here, we'll just project it back to our upper bound. Then we looked at logarithmic barrier, which is also like a wall, but it's just trying to push you away from the wall. And finally, we looked at logistic sigmoid, which you just use to, you map the parameter to an unrestricted one and then try to map it back again afterwards. And we also implemented these three methods. Then the experimental validation. So we had some benchmarks. These were all originally partially observable Markov decision processes, which we transformed into parametric Markov chains. And as you can see, there are many parameters in here. So they are, well, for us, interesting to look at. We implemented everything in our model checker Storm. And we had a 32 gigabyte memory out and a 2-hour timeout. And we used the mini-batch approach with batch sizes of 32. And we asked ourselves the following questions. First of all, we asked ourselves, well, which region restriction method works best for us? Then we asked ourselves, well, which gradient descent method works best? And finally, we asked ourselves, how does our gradient descent approach compare to the existing techniques? So first look at the first question. We looked at the region restriction methods. Here you see it for the momentum sign. So we used the classical momentum gradient descent, where we only considered the sign of the gradient. And on the x-axis, you see a learning rate of 0.1. And we used projection here as region restriction method. And then you can compare it to all the other methods. Where we had the logarithmic barrier and the logistic sigmoid, and we also had it for different learning rates in here. And as you can see, projection actually outperforms the other methods for us. This actually also was for a more sophisticated method like Adam. We had the same results there, which you can also see in our paper. Projection is for us the best region restriction method. It's also the easiest one with the less overhead. Next, we ask ourselves, well, which gradient descent method works best? And here you see we fixed it to projection and a learning rate of 0.1. And on the x-axis, you see momentum sign, and on the y-axis, you see all other methods we had. And each letter corresponds to a case study we had. And as you can see, momentum sign often outperforms the other ones. Notice that we have here a log scale, so it's an order of magnitude at the dotted lines. It turns out that for most case studies, actually momentum sign works quite good. So we decided to stay at momentum sign for the final question. How does gradient descent compare to the previous techniques? Recall that we are looking at feasibility synthesis. So we are interested in finding finding values for our parameters, such that we achieve some bound. First of all, we ask ourselves, well, how do we choose this bound? Because we need to find this. If you make it too easy, so to say, that for all parameter values it's fulfilled, then you're done within one iteration. So that's kind of boring. So we decided to look at two versions for this lambda. First of all, we chose it close to the optimal value, which was mostly present in literature. If it was not present in literature, we just let our gradient descent method run for like 24 hours and then see what value came out. We also looked at those at most 20% away of this optimal value we found, which makes these bounds a bit more relaxed, so to say. So first of all, we compared it to QCQP. You see we have, again, projection, a learning rate of 0.1, and optimal bounds. And we compared it to QCQP. And as you can see, momentum sign often outperforms QCQP. And here you can actually see the different case studies we had. When we relaxed the bounds a bit, it was getting a bit better for QCQP, as you can see, as It's also faster sometimes, but still momentum sign often outperforms it. Next, we looked at particle swarm optimization. Again, first with the optimal bounds, and for the optimal bounds, momentum sign was just outperforming it. And finally, we looked at the relaxed bounds, where you can again see that momentum sign is still working better. So gradient descent often outperforms QCQP and PSO. So what did we see? Well, we compared different region restriction methods. We compared different gradient descent methods. And we show that gradient descent is actually usable to synthesize randomized controllers under this partial observability. And our results were that projection often outperforms other region restriction methods. Classical gradient descent methods outperform the more sophisticated ones where the learning rate is adapted. And momentum sign often outperforms QCQP and PSO. So thank you for your attention.
Yes, I don't see any questions right now in the room. Oh, there's one. 1 second.
Hi, thank you for the great talk. I'm Brendan from McGill University, and I'm curious if you could comment on the benefits and disadvantages of swarm versus other probabilistic model checkers. I guess specifically related to parametric Markov chains and other features that it offers. Thank you.
So I'm not really into the details of particle swarm optimization, but I think it performs better if you're really looking at just a feasible instantiation. And with our case, we really looked, relatively close to some optimal values. So I think particle swarm would be better if you just want to find a feasible, and gradient descent would be better if you're interested in something really close to the optimal.
We don't have any more in-person questions right now.
Maybe I would have one question. You mentioned that syntax-guided synthesis may be related. Do you see a way to incorporate these techniques? Are they relevant for these types of problems?
Sorry, I didn't get the question. The sound is not that good, I think.
Okay, so I wonder. Okay.
Can you maybe just repeat the question? Sorry.
I can try to repeat the question. So, is there a way to improve these techniques using syntax-guided techniques?
So I'm not into syntax-guided techniques, but what we're currently looking at is monotonicity, because in many models there occurs some natural monotonicity, meaning that, for instance, if you have a model of some protocol and you have a channel over which you send a message, then for us it's clear that when you improve the channel, the probability of this message getting received also increases. And what we're currently looking at is how can we actually incorporate this into our approach. So for instance, do some monotonicity checking before you apply gradient descent.
Thank you. And about this 20%, is that sort of, how do you come up with this number? Do you have a sense of in what cases non-optimal results are still good enough for the given application?
No, so we actually looked at both 10, 20, and 30%, and we saw that at 20%, the results for PSO and QCQP were kind of improving. So we decided to stay to 20%, but it's more like, yeah, we just wanted to try it, and we tried different ones, and 20% also looked better for QCQP and PSO.
Okay, good, thank you. Any other questions in the meantime?
Yes, we have one more in the room. 1 second.
I'm sorry if I didn't catch this when you were. So I'm sorry if I missed this, but could you comment on whether or not your problem formulation is convex, and if not, what aspect of it destroys the convexity?
So you mean the gradient descent approach? Or?
Yeah, like is your like problem convex?
So what we're actually doing is we have this parameters, and we just plug in a value. So you're just solving a linear system of equations then.
Oh, so it's a linear problem.
So yeah, so
okay,
that's
okay. Cool.
Yeah, so that's good about this approach, that you actually plug in parameter values all the time, because if you don't do this, then it just explodes.
I think that's all questions from our side. Victor, I think you're muted.
Okay, I can try again. So you hear me now, right?
Yeah, we can hear you. Thank you.
So I was just wondering, you are arriving at different conclusion about usefulness of gradient descent improvements compared to what happens in deep learning applications. So do you have a sense of why this is where this difference comes from?
So you mean why we stick to the classical methods instead of the more sophisticated ones?
Yeah, so
yes. Yes, that's probably, well, first of all, because our models are, well, relatively easy, so to say, from the structure. And we are not interested in finding this real optimal value. So if we go back to to this one, as you can see, we're interested in some value above some threshold. So if you want to find an optimal value, you don't want to jump over the real optimum, because then you have to go back again and search all the time. And for us, it's just fine if we jump over it a bit, because we will probably still be within our range. Yeah, so that's probably why the classical ones, well, they have less overhead and they are sufficient for us.
Victor, I think you're muted again.
Okay, so I have some auto-mute functionality. So